Hello, my name is Saeed Ebrahimi. Today I'm going to introduce our work equality-aware sample-to-sample comparison for face recognition. Recent attempts on face recognition are mainly focused on manipulating the training criteria. Approaches for training a deep face recognition model can be divided into sample-to-sample and sample-to-center loss functions. Sample-to-sample comparison highly depends on the pair selection strategy and requires a sophisticated mining method. In large-scale datasets with thousands of identity and millions of samples, there is a combinatorial explosion in the number of possible pairs, leading to costly pair selection, unstable training, and slow convergence. Therefore, a state-of-the-art face recognition training paradigm are based on the sample-to-center comparison. One major problem with using these type of loss functions is the disparity between training and testing metrics. This work integrates a quality-aware learning process at the sample level into the Angular softmax training paradigm. To this end, we adjust the updating procedure of the softmax centroids to improve the performance on the underrepresented low-quality samples. Three types of samples are presented in face recognition datasets. First, samples that are easy to learn by the model. Second, low-quality but recognizable samples. Third, unrecognizable instances. Prior works have integrated sample-to-sample comparison to the Angular softmax via injecting instance representation to the softmax centers. However, the sampling strategy, which is an indispensable part of every sample-wise face recognition paradigm, need to be considered in them. Studies have shown that the norm of features represent the sample quality. QAFace take advantage of this property to integrate the sample mining to the injection process. The goal is to explore underrepresented recognizable low-quality samples. To this end, instead of using a fixed hyperparameter during the injection, we use an adaptive function, f, to weight the sample's representation during the injection. Before calculating each sample's injection weight, we normalize the representation norm using batch statistics. In this way, samples with magnitude lower than a threshold would not affect the centers. Recognizable but low-quality samples will be emphasized during training, and high-quality samples will receive less attention in comparison to recognizable low-quality samples. We use empty CNN to detect 5 landmarks in each image. Then images are aligned and rescaled to 112 by 112. We adopt result 100 for the backbone. This table shows the performance of our model in comparison with other state-of-the-art methods. We plot the loss value for a fixed imposter cosines, while the genuine cosine changes from -1 to 1. The observation here is the monotonicity of the gradient among the hard samples. In other words, some samples are unrecognizable and have negative genuine cosine. However, their gradient is equivalent or more than those of informative but hard samples with positive genuine cosine. QAFace tries to compensate for this effect by ignoring the unrecognizable samples during the injection.